Yeah, good morning to all of you. I hope I'm audible.
Good morning, sir. Yes, sir.
Good morning, sir.
Good morning,
Good
sir.
morning, sir.
Good morning,
Okay.
sir.
Okay. So let us start discussing the basics which we have been talking about. So in the previous lecture, we discussed about some generic terminology that we use in remote sensing. Okay, and then we started discussing about background of geoinformatics and what are the fundamental divisions of geoinformatics and what are the component that you need to learn. Okay, so we have a two fundamental division of geoinformatics. The first one is measurement of geoinformation. As you know that geoinformation is measured in terms of geometric as well as radiometric information content. Okay, so when we talk geometric information, it includes shape and size of the object, position of the object, where it is located. And when we talk about radiometric information, it is related to the pixel value. Okay, or it is related to the color information associated with the remote sensing data. I have shared my screen. This is it visible at your end? I hope
No,
one
sir, it
message.
is showing that can't display content.
Is it with all of you?
No, sir, is visible to us.
Yes, sir.
Fine.
Visible.
Fine.
Visible, sir.
Okay.
No, sir. Not visible.
So could you please check out your bandwidth? There might be some, this issue might be due to the low bandwidth at your end. By the way, I am just explaining the content. Okay. So just listen that if it is not coming right now at your end, it may take time and it will appear at your end. Or you could do one thing like just log out and log in again, so that screen might reflect at your end. This could be done. Okay, we can wait for 1 minute. Sumit, now let me know. Is it coming?
Yes, sir, now it is coming. I have left
Okay.
once, resumed, then it is coming.
Yeah, fine. So if all of you can see the screen, then just I'm talking about this fundamental divisions of geoinformatics. The second category, that is a management of geoinformation. Okay. So in the management of geoinformation, once we collect the data, okay, then we store the data, and further for the application that we are going to deal with processing that data, we need to go for retrieval of different information, object information like road network, building, okay, etc. So these specific object information needs to be retrieved, needs to be identified. Okay, then they can be presented using GIS tool. Okay, and later on we'll do the manipulation, like based on the available information. We do some manipulation and further we present it. Okay, so overall aim is to process the remotely sensed data to solve the objective of different applications. Let's say if our aim is to just digitize the road network, okay, and so what we need to do, by processing the images, we need to identify the road network first. Okay, so that road network information is retrieved, it can be separately presented. Okay, and each road pixel also include its position from where that pixel is acquired. Okay, so what is the 2D location of that road network? Okay, and further analysis can be done for the related applications. Like let's say if I share with you one example, in case of flood scenario, okay. So if there is a rescue operation, so they should have a map, road network map of the city, okay, along with the information of different locations, the elevation value, okay. So what is the height of different locations in the city, okay, based on that information as well as the road network. They have a GIS database of the road network, so they can quickly plan, okay, they optimize their rescue plan based on this information available with them. Okay, obviously you should have information of route, and that plan could be done in optimized way in the office, okay, by applying certain algorithm. This can be done. Fine. So just see the hierarchy for this application. What we want first we need to have a remotely sensed data of the city or of that area, okay. Then after that, if that remotely sensed data is image, then you need to identify the pixels and their locations, okay, which belong to the road network by applying certain algorithms. Then that will be as well as map, okay, where what you need to do first, the digital out the height of different points on the ground terrain. So there we do not consider. So in the image itself, what you need to do, you need to identify the ground pixels first, okay, and you get the digital vision. So digital vision model tells you like if that flood originate from some water source. Let's say if there is a river in the city, source from where flood originates, okay. So how quickly that flood spread in the city, that is decided on the basis of city, okay. So that info the road network information that is for the optimized route planning, like okay. So based on that map height map of that area, the optimized route planning can be done, and related activities. One example. Similarly, we have many, okay, where the same procedure is followed. Now I'm coming back to this tools, how we collect the geo information, how we measure geo information. So when we talk about earlier, they used primitive
सर फेस ब्रेक हो रही है.
hand. Sumit, I hope able to most of you.
यस सर, आपकी वॉइस ब्रेक हो रही है.
Okay. Is it? Am I clearly audible now? If this problem will still persist, so kindly remind
Sir, it is
so they
still
are
breaking.
facing hands. Okay, so we are discussing about measurement tools which were used in the earlier days. So there were primitive techniques whereby using your hand, by some type of guess, by using a standard rods and some Patwari measurement methods, human figure were used. Okay, but these techniques have a lot of limitations because they are not very fast. Okay, they consume a lot of time for the measurement as well as they are labor intensive, and even you can't use these techniques. First you need to clear the space for using this technique for measurement. Okay, then later on, if we talk about the technology improvement, then land surveying techniques, some traditional land surveying techniques came into the picture, like using chain and compass. Using chain, the distance measurement were done, and using compass you could able to measure the angle from certain reference direction. Then the electronic version of compass was came into the picture in the form of theodolite. Okay, but again these methods are very cumbersome and cannot be used in inaccessible area. Let's say in a mountainous region you want to do some measurement, you want to measure the distance between 2 points, and so because if you are going to use a chain for the measurement, so two persons need to hold the two in the of the chain, you need to straight it, then you can able to do the measurement. So it is again can't be done in the inaccessible area, very crowded place where you can't have a clear zone, and obviously there is a substantial human dependence, so they are quite labor intensive. Then further advancement was done in the technology side. Okay, and the electronic land surveying techniques were designed, like EDMI and total station. So the EDMI is an electronic distance measurement instrument that is used for measuring the distance between 2 points. If some of you are from the civil engineering background, so I hope in your undergraduate laboratory you used EDMI and total station. How many have used already, have a kind of experience on these two instruments?
No experience, sir.
Yes, Shivam, you raised your hand. Would you like to speak? Yeah.
Yeah, sir. I used.
Yeah, fine. Generally, the undergraduate laboratory course of surveying, these instruments are used. Okay. So briefly, if I consider the EDMI, so in EDMI there is an internal energy source. Okay, that is a laser beam. And once you switch on the instrument, a laser beam is fired from the laser source. It travels in a straight line and hit a target point where you focus it. Okay. Again, there is a return signal. Okay, and that return signal is sensed by the EDMI sensor. Okay. So based on the beam transmission and reception, the distance is measured. Okay. When we talk about total station, so total station is a composite version of EDMI and theodolite. It means using TS, you could do the measurement between 2 points, as well as you can able to measure the angle of a point that is connected to the this total station. If you connect a line of a point from the total station and the reference line, so angle between these two lines uh, can be measured by total station. Nowadays we have a further advancement in the technology of TS, where we have a robotic total station that can automatically target the point. Okay. So in this semester, I hope there will be a kind of simulation. There will be the theoretical discussion on these instruments, how they are used for the surveying. Okay, a topographic mapping. Compare with the primitive techniques, some other traditional methods. This electronic way to do the measurement is fast and accurate. Okay, but again, it is a it is a difficulty. It is not possible to access the inaccessible area. Okay, and from here you want to acquire the point. So again, there will be the accessibility issues with this instrument. So briefly, we discussed the fundamental background, how using TS you can do the coordinate measurement of a point. Okay. So first we understand the measurement that we get by using theodolite and EDMI. Then we'll see how using theodolite and EDMI, they are comprised in one unit that is resulted into the total station, how they work. Okay. So first we define a coordinate system with reference to the instrument. Okay. Generally they're defined at the optic center of the instrument or at a point within the instrument. Okay. So X, Y, and Z axes are defined with the origin location. So the first, it's a general concept, how we define a coordinate system. Then we define a coordinate system by fixing the location of origin where it is. Then we see what are the directions of different axes. Okay, we define the direction of X, Y, and Z axes. Whether those directions are defined with reference to some, let's say, some reference lines. Like a reference line could be the north axis of the Earth. Okay, when we collect center of mass of Earth to the North Pole, so that can be a reference line. Okay, with respect to that, we can define the axes of coordinate system. Even another global, this reference line could be, if we consider the Earth's surface. So there are various axes when we consider the meridian and equator. So intersection point of prime meridian and equator, if you recall the concept in from geography aspect. Okay, so you have already read that how the Earth surface geometrically defined. Okay, so there we define different circles like prime meridian, that is a circle passes through north and south pole, and the Greenwich line. Okay, and then we define equator. So the intersection point of prime meridian and equator can be considered at one point, and it is extended to the center of mass of Earth. So that line can also be used as a reference line. Okay, so we have discussed about two reference lines, like line connect north pole to center of mass of Earth. Similarly, the line connects center of mass of Earth to the point, the line that connects center of mass of Earth and point of intersection of prime meridian and equator. Okay, so these are certain reference lines which are defined with respect to Earth surface. Okay, so those lines can be used as a reference to define the axes of the coordinate system, are are in a local coordinate system. Even these lines can be defined. Okay. So once we have fixed the direction of three axes and we have fixed the location of origin, okay, the coordinate system is defined. Okay. One more parameter we include over here, that is whether it is right-handed coordinate system or left-handed coordinate system. Like in this diagram, if you see that if you move from x to y axis, then your thumb direction will be along the z axis. If we use your right hand and if you apply the right hand thumb rule, you have already read in magnetism, in physics. So if you orient your fingers from x axis to y axis, then obviously your thumb will point towards z axis. So then we can say that it is right-handed coordinate system. So now we have defined the coordinate system. Now our aim is to locate various points within this coordinate system. If you want to go for the topographic mapping, okay, if you want to close a particular contour, okay, so how you can proceed using the electronic instrument. Let's say you have two instruments with you, EDMI and theodolite. How it can be done? So what you need to do, let's say you select a particular point. At that particular location, you need to install your instrument. And from that location will be at the origin where you define the coordinate system. From there you start. Okay. Now the next point you need to target, and you need to measure the coordinate of next point in the defined coordinate system. So what you do, from the origin of the coordinate system, you target a particular, let's say, point P1, and you measure the distance. Okay. Similarly, if you measure the distance, then similarly using the theodolite, you need to measure two angles from the vertical axis and from the horizontal axis. Like in this case, theta is measured from the vertical z axis and phi is measured from horizontal x-axis. Okay. So these principles are combined in total station, where when you point a particular target, okay, by using the total station, where internally this XYZ coordinate system is defined, okay, then a laser beam is fired that hit that point, target point P1, okay, and that range R is measured. Similarly, the total station also measure the two angles theta and phi. So R, theta and phi, these three parameters are computed, okay, then you can further estimate this coordinate in Cartesian coordinate system. Okay. So by using R, theta and phi, you can also get the component along x, y and z axis. And this component will give you the coordinate of point P1 in Cartesian coordinate system. Cartesian coordinate system means measurement, distance measurement. What is a projection? If you project that point on z axis, if you project that point on x axis and y axis, what will be the length? And actually that is the coordinate. But if we consider a total station based survey, so it is again very labor intensive. Let's say if you want to map, if you want to make a map of, let's say, 200-kilometer road network, okay, and if you want to do it using total station, it is not feasible. Okay, because when we talk about the mapping based on total station, then there will be the requirement of two person over there. One person need to handle the total station, another person need to hold the prism. and for each measurement you need to initialize the instrument, and it's a ground-based survey, so it will take many days to complete the survey. Then there was the requirement, and which was felt, like, can we have a platform like aerial platform? Okay. Then aerial photogrammetry came into the picture, and where aim was to capture the images, capture the photograph from the aerial platform, so that in short span of time we could cover the large area. So this technique emerged during World War I and II, and it was used during those days for the military purposes. And if you recall, initial uses of pigeon with camera to spy enemy terrain, when there was not an aerial platform. So in that time, camera was there, and it was attached with the pigeon, and it was used for the military purposes. So overall motive is to have a larger field of view. How we can obtain the larger field of view? When we see that entire area from a large distance without obstruction. Because we can't get a larger field of view from the ground-based platform, but there is a lot of surrounding obstruction. But once we look towards ground from the just above the earth surface, okay, if we look from the air, then if you increase the distance, then area coverage, that is a field of view in which that camera can focus, will increase. Then obviously at the same time you need to increase the this megapixel capacity of the camera, so that you will get a good quality of image. Okay. So in aerial photogrammetry, the different platforms were used, like balloons, then later on aircraft were used. Now further, let's say single photograph were collected for the interpretation. Then further, due course of advancement in technology, uh, there was the provision to generate 3D model using the images. Okay. As you see in the right side image, there are two photographs, but they are overlap. So by using that overlap information, the three-dimensional model of that terrain can be generated. As you know that in a particular image or photograph, there is only two-dimensional geometry information as well as the pixel value. The pixel value gives you idea about the type of feature on the terrain. Okay, there is not the depth information available. Okay, so to get the depth information, or we can say the 3D model, by using the stereo photographs, where each successive photographs has the overlap area. Okay, so that is used and processed through the algorithm, and 3D model was developed. Okay. So now we see the uh, workflow of technology advancement in case of photogrammetry. Then in the beginning, analog photogrammetry came into the picture. Later on, advancement took place to develop analytical photogrammetric technique. And nowadays, we have a digital photogrammetry. Okay, but still, we need to fly to collect data every time. Each time you need to plan the airborne survey. Okay, and you need to fly, then you collect the images, and further that images will be used for the applications related to that. And again, there is a cons using this technology. Like it's very costly affair and may not be possible in bad weather. So to do the aerial photogrammetry using aircraft, first you need to plan the airborne survey, and also you need to assess the environmental condition. It can't be done in the bad weather. Okay. Now, considering the limitations of different remote sensing techniques, in later days, satellite remote sensing was evolved. Okay, and commercially it came into the picture in 1972. Okay, so the satellites were sent around to rotate around the Earth's surface in the altitude of 600 kilometer to 900 kilometer. Like in case of Landsat satellite program, the images which was collected, those images had a resolution of 80 meter. It's not quite impressive, like 80 meter by 80 meter. That is the ground area element size for which a unique pixel value is assigned. Okay. In this slide, you can see the pictures which were collected to the aerial platform. Sorry, they were collected to the satellite-based platform. Okay, and they are photographed. So to get a synoptic view of terrain regularly in several wave bands, the most feasible technique is satellite remote sensing, by using which we can get a spatial resolution from kilometer to meter. It is again depends on the which spectral band you are using and for what purpose you want to use that image. Okay, let's say your objective is to go for very precise measurement of information. Okay, like if you want to go to detect the building boundaries. Okay, obviously in that case the spatial resolution should be better. You can't go for the building detection, building boundary detection, outline of the building using the image where spatial resolution is, let's say, in few meter. Okay, obviously for that purpose at least it should be in sub meter level. Okay, and like in case of satellite remote sensing, no need to fly, no need to again plan the airborne survey. Okay, and no need to wait for the clear weather. It can be regularly done irrespective of type of weather. Okay, and you could have a synoptic view of terrain regularly. Okay, and even the very large number of bands are used. Okay, to have a very clear and precise information about the objects. Okay, so again moving ahead in this discussion, when we talk about a several wave band or spectral band, means the Earth surface objects reflect the energy in very large, very wide band. Wide band means entire electromagnetic spectrum is covered from visible band to microwave. So in this very wide wave band, okay, certain discrete bands, spectral bands are selected. Okay, and in each spectral band, the response of same material differs in terms of reflectance. Okay, let's say if we consider a tree, or if we consider a grass field, Okay, and the grass field that grass field image is acquired at spatial resolution of, let's say, 5 meter by 5 meter. Okay, so one area patch from the ground of 5 meter size, there is a reflected energy coming out from that grass field, but that is, the magnitude of energy at a different band, they are different. And this is one of the very important parameter which is analyzed in a different way in the different spectral bands. Okay, energy coming out from each spectral band is different from the same object, and this will give you very detailed information about that object. We will discuss about it in the coming lectures, like how we exploit, how we use that object information in terms of reflected energy that vary with respect to wavelength. Okay, for the identification of object, classification of objects. Okay, and why it is very important in remote sensing. Fine. So several wave bands means it could be possible we collect the images in one particular only one band. We can even go for 5 to 12 bands. Even further, we can extend the number of bands till, let's say, 200 to 100 to 200 bands. So similarly, on the basis of number of bands which are used to collect the image, we categorize the remote sensing technique into various categories. So this is one of the parameter that is used for the categorization of remote sensing, satellite-based remote sensing technique. Okay. So the images which we collect using satellite-based remote sensing, those images can be used for both measurement and identification. So depth, if generally in satellite-based remote sensing, the images do not have the depth information. They only have the location of the pixel, okay, and the characteristic of the object in the form of pixel value. So the distance between the objects can be measured, okay, as well as their properties from which class they belong, that can be identified. Okay, this is an example of repetitive data, like in using the remote sensing technique, satellite-based remote sensing technique. At the regular interval, you can acquire the images from the same area. Okay, so that is a temporal information available. So by comparing the images acquired at two different time, the change detection can be done. Like how much changes incurred during that period. Let's say in a particular year, you have an image of Jan month. Okay, and after that you have another image in July month. So after the 6-7 month interval, you get another image. By comparing the change in pixels, you could able to determine, you could able to figure out the changes incurred in this 6-7 month duration. Okay. Now we have another remote sensing tool. It is very important and it is used for measurement of location. Okay. And it is called as Global Positioning System. A generic name is Global Navigation Satellite System, GNSS. So an absolute new concept, and that has been used for locating a particular point, particular object. Okay, and it evolved first sending the 24 satellites around the Earth. Okay, and they rotates in a fixed orbit. So if you want to measure a particular point coordinate by using the concept of coordinate geometry, we have already discussed how to define a coordinate system. Okay, so in the same coordinate system, if you have a three known points means those points coordinate is known, and designate them as P1, P2, and P3. So the point P1, P2, P3, their coordinates are known in a defined coordinate system, and there is a fourth point, and it is unknown. We don't know the coordinate. How? By using the information of three known coordinates, you can able to measure the coordinate of fourth point. If you recall the coordinate geometry concept, okay, then we can do what we can do. We can just connect the unknown point from the known point's coordinate. Okay, so once the known points are connected with the unknown point, just measure the distance. What is the distance of point P1 from P0? P1, P2, P3 are the known points, and P0 is the unknown point. So measure the distance between P1 and P0, P2 and P0, and P3 and P0. Okay, and just write the equation. So distance is known, and that is equal to square root of x1 minus x0 square, y1 minus y0 square, plus z1 minus z0 square. Similarly for the point P2 and point P3. So you have a three equations, and there are three unknowns: x1, x0, y0, and g0. So these three unknown points can be measured using these standard equations. The same geometry concept is applied over here in GNSS based positioning measurement. Satellites are revolving around the Earth's surface. They are continuously sending the signals towards Earth's surface. Let's say if you place receiver somewhere, that receiver get the signal from a satellite. Okay, and that signal contain the location of the satellite in a reference coordinate system. So there is a common coordinate system which is defined, and signal is sent by the one satellite P1, second satellite P2, and third satellite P3. Even fourth satellite, why it will require, will be discussed later on. So three signals from satellite P1, P2, and P3 are received at P0 location, and that signal contain the distance from P0 to P1 at that time, P0 to P2, and P0 to P3. Same concept apply over there, and that point coordinate measurement can be done. Okay, and we define a coordinate system. Geocentric or geographic coordinate systems are used for global navigation satellite based positioning measurement. Okay, so geocentric coordinate system, where we select origin at the center of mass of Earth, and we fix the direction of three axes with respect to the reference line that I discussed before. That line passes through center of mass of Earth and North Pole. The line passes through center of mass of Earth and intersection point of prime meridian and equator. So this is a brief introduction about how GNSS work, and there will be detailed discussion in geospatial data processing course, as well as in the second semester you will have a specific course on GPS. So there you will learn in detail what are the various concepts of GPS. So just see over here, around the Earth's surface, there are a constellation of satellites, and they are evolved in the fixed orbit, and they are continuously sending the signal towards Earth's surface. So minimum 4 signals are required to locate a point. It means 4 signals means you need to have a 4 satellites should be tracked, and the signals coming from 4 satellites, those signal will have a location of satellite as well as this what is the time at which the signal is sent. Okay, time as well as the location of that satellite. So when you go to collect the positioning data using GPS, if you move very fast using the GPS receiver, then it is less accurate. Okay, and if you put a GPS receiver for, let's say, half an hour at one place, then in that case it will be more accurate. So it all depends on application. So if the static operation by using GPS will be more accurate compared to the dynamic operation, and it can be done everywhere. And as the requirement is that you need to see the satellites, that position, that receiver should have access to the satellite signal. It means there should be a clear sky, and there are thousands of applications, and like all of us, we know that navigation related all the applications are dependent on GPS or GNSS technology. So now I am stopping my discussion over here. If there is any query, so you can discuss with me, like 4 minutes are left. Otherwise you can note it down and you can put it into the next session.
Sir,
Yeah.
sir, there is a curiosity to know one thing, sir. The picture you shown in that title under satellite remote sensing, in
Yeah.
which continent was shown. Sir, can we generate such kind of image where we can have a large information like we when we see a picture,
Mm-hmm.
the continent is being shown, and if we zoom it, then different countries are shown, and if we zoom it more, then different states of that country is shown. Can we generate such kind of image?
I think Google Earth application, we do the same thing.
That do the same thing, but can we generate it as a image wise?
No, Google Earth, they are the images, and
Okay.
it is all GIS database. If you
Okay, sir.
if you zoom it, then you can see the very finer detail.
That is obvious, sir.
Okay, so Google Earth, it's an example.
Okay, sir. Thank you, sir.
Okay, so if there is no further query, I stop my session over here. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.